Here we are starting up an R410A system with a thermal expansion valve, and our pressures go from equalizing to settling in, and they're going to settle in at around 110 psi on the suction side, about 225 on the liquid side, and our subcooling for this unit is right at 8 degrees, right where it should be. Now I'm going to create a problem. Now watch the head pressure as it rapidly starts to increase. And our suction pressure is kind of lagging behind a little bit, but nothing crazy. But that head pressure keeps rising. And we settle in at around 325 psi. Now you can see our saturation temperature is about 100 degrees. And when we look at our liquid line temperature, our subcooling has now increased to 14 degrees. Meanwhile, our suction pressure starts to drop off rapidly. And it just keeps dropping below the normal pressures that we're used to seeing. And eventually it drops off well below that freezing point of water, and now we have problems. Now the problem I created was that I cut off airflow to the condensing unit. As technicians, we're usually not fortunate enough to walk up and actually watch all this happening. We just end up with the end results. We have a low suction pressure, head pressure is a little bit high, maybe even normal, and our subcooling has increased well beyond what it's rated to be. So why do the pressures change on our gauges when we have problems? What's actually happening when these pressures change? And how can we start to read this information to learn how to see problems that are typically invisible and not so obvious? Like this. When we add heat to refrigerant, the molecules that it's made of pick up a whole lot of energy, and they start moving with purpose. They start bouncing off of each other, they're bouncing off the walls. It's like some hardcore concert where everybody's just moshing and beating the snot out of each other. And we see the result of this by an increase in the pressure on our gauges. When we remove heat from the refrigerant, the opposite happens. These particles, they start mellowing out, they get chill, maybe sing a little kumbaya, and we see the result of this activity by a drop in the pressure on our gauges. So the changes in pressure we're seeing on our gauges are signifying that we're either gaining heat or losing heat somewhere in the process from wherever we're measuring those pressures from. And if we see abnormal pressures, high or low, that's telling us even more of that is happening in that location. So let's go back to our condensing unit where we created the problem. Now when an air conditioning system is running properly, what's actually happening is the air is being pulled in through the sides, and there's this tight section some midway into the coil where the hot vapor refrigerant is very quickly flashing over into a liquid. And that quick transformation process creates a very solid column of liquid from that point on. So we have solid liquid throughout the remainder of the coil going all the way up to the TXV valve. Now that solid column of liquid is very, very important because that is what creates a pressure differential on both sides of the metering device. And that pressure differential is what actually moves the liquid refrigerant through the system. It's not the compressor, it's that pressure differential. When we blocked off the airflow going through the sides, what happened was that we took away that tight little zone where the refrigerant was flashing over into a liquid very quickly, and we completely spread it out because that refrigerant was no longer rapidly cooling off. That's why we saw an increase in our head pressure. Now, just because we're not moving air across the coil does not mean that refrigerant isn't going to condense in a liquid. It still will. It just does it by different means. It'll give off the heat to the surrounding atmosphere one way or another. And so that refrigerant does still condense. But instead of that tight little midsection, it's now happening across the entire coil and all the way up to the TXV. And that causes us to lose that solid column of liquid refrigerant across both sides of the metering device that creates the pressure differential that allows that liquid refrigerant to move. And so what happens is that refrigerant, some of it gets left behind and trapped on the condenser side of the TXV. And for that reason, it actually sits in the coil longer and has more time to cool off. And that's why we saw an increase in our subcooling. Now, while that process was occurring, we also saw a slight increase in the suction pressure. And so what was happening there was because all that refrigerant was retaining a lot of heat at first, that created a greater pressure differential across the metering device. And so what that did was force the metering device open a little more, feeding more refrigerant into the evaporator coil, and that's the pressure increase we saw. More refrigerant, we can absorb more heat, and the pressure started to increase a little bit. But then we saw that pressure drop off pretty hard. And what was happening then was that solid column of liquid broke down. We lost that pressure differential across our metering device, and then we started to starve the evaporator coil. And with less refrigerant, our temperatures dropped, we had less ability to absorb heat, and so our pressure started to decrease.